All right, so this is Unit 6, Day 2, vertical and horizontal particle motion. If you're trying to keep up, it's the 24th, which is a Tuesday. All right, vertical and horizontal particle motion. A lot of notes on the first page, not a lot of things you got to write, but a lot of things you got to know. So hopefully you still have a pen in hand because we'll annotate a little bit as we go. In general, t is time. In theory, t can represent some other value. It's almost always going to be time for us. I think I could say it's always going to be time. So pay attention to each problem's t. To each problem's t restrictions. If t represents time, can t be negative? Well, there's the answer right there. Yes. Although I would more likely say it depends. Like maybe. Just depends on the problem. If you're running some experiment and you start the experiment at time 0, then negative time probably wouldn't make much sense. But here's the example where it would work. If t equals 0 represents noon, what value of t would represent 2 hours before noon? Well, t equals negative 2 would be 10 a.m. And maybe that would be fine to figure out what happened at 10 a.m. So sometimes you throw out the negative t's, sometimes not. Depends on the problem. Read carefully. S of t is frequently used for position function. Other variables can be used. By the way, there's a whole bunch in common with physics today. So I don't know if that's good news or bad news for you, but a whole bunch of things in common. X of t is often used for horizontal motion. Y of t is often used for vertical motion. I think in physics, in our physics land anyway, a lot of times we use dx and dy. Does that look familiar? That's the same thing, like distance in the x direction. So in here, in calculus, if you say dx, we're starting to think about derivatives. So we kind of avoid the dx and dy stuff. But x of t in here means the same thing as dx in physics. And so in physics you use dy. In here we'll just say y of t. So those are interchangeable. V of t equals s prime, the velocity function. Another way to say that is ds dt, or s prime. So there's a connection between velocity and position. A connection that you don't really make in the first year physics class. The second year physics class, you definitely make that connection. But if you only took 1 year of physics, you probably didn't talk about velocity as the derivative of position. But now that you know about derivatives, we can introduce that. Acceleration is the derivative of velocity, so that would make it the second derivative of position. Hopefully some of this meshes with physics, right? Like ds dt, that would be like meters per second. And acceleration would be the change in meters per second over second, so that's meters per second squared. So again, with the units, they can help you figure things out. Here's another kind of parallel with physics. What's the difference? Forget this. Just tell me from physics, what's the difference between speed and velocity?
Velocity has direction.
Okay, velocity has direction. That's what we say in physics. That's right. And speed doesn't have direction. We just peel off the 30 degrees north of south stuff. Well, in here we're not concerned about like cardinal directions like north and east and 45 west of north and all that stuff. But the sign tells you direction, right? The sign would mean you're going backwards. So for us, speed is the absolute value of velocity, and that absolute value will kill off the positive or negative, and it won't have a direction anymore. So for us, speed is the absolute value of velocity. That's what takes care of the direction. Number 4, the particle is at rest when velocity is 0. You definitely hit that in physics, right? Because the problem would say a ball is dropped from the top of a building and you would know that dropped means at rest initially, velocity is 0 initially. Particle moves to the right when velocity is positive. Particle moves to the left when velocity is negative. That makes sense, right? It matches the coordinate plane. Positive is up or right. Negative is down or left. All right. Another parallel with physics is displacement versus total distance. Displacement is just where you are relative to where you left, right? The classic example is if you run around the track one time and you end up exactly where you started, what was your displacement? 0, right? In fact, you could run around the track 100 times and your displacement would be 0, because where you started relative to where you ended, it's where you ended minus where you started. And so it doesn't matter how you got there. When we get to calculator land, we'll use this symbol, but we're not really there yet. Total distance, obviously that's different, right? Because if you run around the track 10 times, that's 4,000 meters. That's a long way. That's very different than displacement. So we have to be very careful with distance. It's always positive, right? If you ran around the track backwards, it's still 400 meters that you covered. Whether you actually ran backwards or is there a right way to go around the track and a wrong way to go around the track? I don't know. I'm not track. You're saying yes, there is. Okay. So if you face the other direction or ran it, it's still 400 meters around the track. It's like in NASCAR, you always make left turns. Is it the same on the track? Okay. Now I'll always know. It's the NASCAR connection. We'll get to an example of displacement versus distance in a minute. It will make this make a little more sense, I think. But right now, your physics knowledge is really helpful. Displacement is just where you ended minus where you started. Distance, you got to be a little more careful. How did you get here? Right? Your displacement from here to Riverwood is whatever, 1.5 miles. But what distance did you travel to get there? It's how did you get there? Did you go straight there, or did you wind around a little bit? So distance versus displacement. Define when the speed is increasing or decreasing. Right, this is something that doesn't really have a physics equivalent, at least certainly not that you deal with in first year of physics. So this is calculus only thing. Well, I shouldn't say that. I mean, it's all related, but the way we phrase this is definitely calculus specific. You can sort of skip over this explanation. Here's the big news. The particle is speeding up when velocity and acceleration have the same sign. The particle is slowing down when they have different signs. Okay, so if you're moving forward and your acceleration is positive, then you're getting faster in the positive direction, you're speeding up. If you're moving backwards and you're getting faster in the negative direction, this is a little bit confusing. Your acceleration is negative because you're speeding up in the negative direction, you're speeding up. What's tricky is when something like if velocity is negative, so you're going backwards, and your acceleration is positive, so you're going backwards, but your acceleration, your change in velocity is headed in the right direction. That means you're going from negative 12 to negative 9 to negative 6 to negative 3. Acceleration is positive. That would mean you're slowing down. Which, if you attach this to your car, things get confusing. If you're in reverse, you're backing out of your driveway, You get to the end. You press the brake because you want to slow down, right? You don't want to run into the neighbor's mailbox behind you. Hopefully no one's done that. So you press the brake to slow down, so you know you're slowing down. But if you're going backwards and you're pressing the brake, is your acceleration positive or negative? So your velocity is going from negative 12, negative 9, to negative 6, to negative 3. Like you're slowing down, you're pressing the brake, but your acceleration is positive. So it's just a little bit weird. Like you can press the brake, and if you're in reverse, your brake is now your accelerator because of the signs. So this is where we can try to trick people on the test. Right? If you're going backwards and you press the brake, you're accelerating. Well, accelerating usually we mean speeding up, so we would say your acceleration is positive. We should just phrase it like that. Joseph? If you're going backwards, if you're just starting out going backwards down the driveway, so you press the gas pedal, and so your velocity is negative, you're in reverse, and your velocity goes from 0 to negative 3 to negative 6 to negative 9, so you're speeding up. What is your acceleration? Negative. So you're pressing the gas pedal and you're getting a negative acceleration. But the reason is you're going backwards. Now, that's just the confusing part. The easier part is just look to see if they have the same sign. If they have the same sign, then you're speeding up. If they have opposite signs, then it's like they're fighting each other. The velocity wants to move forward, but the acceleration is pushing it backwards. That's a slow down situation. If you're going backwards, but the acceleration is positive, they're fighting each other, you're slowing down. All right, let's work a problem with 9 parts. Some of these parts are very easy, though. Easy for me to say, right? Example number 1, no calculator. The position of a particle that is moving in a horizontal line is given by the equation S of t equals all of that, where t is measured in seconds. T is greater than 0, so we don't have to worry about negative time. S is in meters. Find the velocity of the particle at time t. Okay, so how do we find the velocity if we know the position? Flip it back over, take a peek. Hopefully it's boxed on the previous page. How do we find velocity if we know position? Take the derivative. So let's take the derivative of position. No popsicle sticks, so I just have to call on people. Parker, what's the derivative of position?
3t squared minus 12t plus 9.
Good. So that was a pretty easy one. We had an easy equation. We know velocity is derivative of position, so no big deal. How about the velocity at 2 seconds? How are we going to find that? Velocity at 2 seconds. Plug it in where, though? Now I got S and V.
For t.
Plug it in for t into the S equation or the V equation?
The equation?
The V equation, right? If you want velocity, plug it into the velocity equation. Oh, that's a safe stop, so let's leave it alone. And then velocity at 4, same thing. Make sure you go to the velocity equation and plug in t into the velocity equation. And safe stop, because I don't want to mess this up. Leave it alone. find the acceleration at time t and at 4 seconds. So question C sort of combines A and B instead of doing them separate. Just find it and then plug in 4. So Andrew, how about the acceleration? How do I find the acceleration first of all?
Take the double derivative.
Okay. Now the good news is I already have the first derivative. So if I take the derivative of velocity, I'll get acceleration. So what's the derivative of velocity?
6t minus 12.
Good. And then at 4 seconds means plug 4 into acceleration. Be careful, now we got 3 equations working with here. So be careful when it's time to plug something in. Make sure you put it in the right spot. 24 minus 12, I'll do that one. I mean, I could have safe stopped it, but I can handle 24 minus 12. You know what? Now that I have S and V and T, maybe I should sort of, because there's nothing else we're going to be using. S, V, and A. Position, velocity, acceleration. The rest of my questions are going to have to do with those 3 things. When is the particle at rest? So what does at rest mean? V equals 0. In fact, I think we just justified our answer. At rest means V equals 0. So let's grab our velocity equation and set it equal to 0. They were kind to us. They gave us one where the 3 will factor out, and then the leftovers factor pretty easily. So t equals 3 and t equals 1. Solving for t, this is a spot where you could get a negative t, right? If they had rigged this to factor a little differently and we got t equals negative, this would be one where you could throw out the negatives because we're only looking at positive t. All right, when is the particle moving to the right? When is the particle moving to the left? Well, moving to the right, what does that mean?
Velocity is positive.
So velocity is positive. Moving to the left, velocity is negative. So we've mostly justified our answer. We don't even have an answer yet, but we know what we're looking for. Okay, well, we know where velocity is 0. That's 1 and 3. So let's do that number line thing that we've done before, where we'll test some intervals to figure out where velocity is positive and negative. So I'm going to plug in 0 and 2 and 4 into velocity because I want to know which way we're moving. So V of 0 is 9. So that's positive. V of 2, we did that already, except we sort of cheated ourselves here. We safe stopped it, but now I need to know what that is because I need to know if it's positive or negative. So I need to go back and 12 minus 24 plus 9. That would be negative 12 plus 9 is negative 3. I don't care so much about the 3, I do care about the negative. And then, hey, life on the edge, if I plug in 4, is it going to be positive or negative using my alternating rule? Should be positive. I have V of 4 up there, so I should probably go check, but I'm just going to alternate. When does the alternating rule not work? Double roots, or quadruple roots. They're even roots. Okay, let's make sure we answer the question, because this picture doesn't really qualify as the answer. I need to give a better answer. So we're moving to the right. Here and here. So what does here and here mean? Moving to the right when V is positive. You can do this in inequality notation or in interval notation, either one. I'm going to go with intervals. I think it's easier. So from 0 to 1, we're moving to the right. And then from 3 to forever, we're moving to the right. Moving to the left, that would be where V is 0, or excuse me, where V is negative. So that would be from 1 to 3. But you can see with this picture how this relates to what we were just doing. We took a first derivative, we set the first derivative equal to 0, we put those on the number line, we tested the intervals, and that's where we saw where S is increasing, decreasing, increasing. So we're doing the same thing we've done the last couple days. We're now just applying it specifically to position and velocity. All right, part F. I guess part F is tricky because it's new. It doesn't attach directly to what we were doing previously. We're going to draw a diagram, but it's not a graph like we normally think of it. We want to draw a picture of what the particle is doing. So let's see. And our moving right, moving left stuff can help. So we start at 0. Let's get some key times and some positions. So 0 was a key time, 1 was a key time, and 3 was a key time. Meaning those were 0 because that's where it starts. 1 and 3 are where it changed directions. So S of 0 is 0. That's an easy one. S of 1. I'm looking back at the S equation now. 1 minus 6 plus 9 is 4. And then S of 3. 3 cubed minus 6 times 9 plus 9 times 3. 27 minus 54 plus 27, back at 0. Okay, the motion diagram is, again, it's tricky to do. We're going to start at t equals 0, which happens to be s equals 0. So you'll always start, I guess I shouldn't have circled the second 0. Always start at t equals 0. There's my starting point. And then from 0 to 1, if I'm going from 0 to 1 in time, I'm going 0 to 4 in position. We already know that's moving to the right. So I'm going to move to the right, and somewhere over here, at time equals 1, I'm at position 4, because I was moving to the right between 0 and 1. The motion diagram is an attempt to put time, position, and velocity like all in one picture. So time and position, and velocity is sort of the arrow that connects the two. All right, well, at time equals 1, we're going to turn around and go the other way. So if we just laid it right on top, that's actually what's happening. It goes this way and then it goes back. But if I drew an arrow backwards, that would be confusing looking. So we're going to drop down a little bit here. Head back the other direction. This is still t equals 1, s equals 4, which means I wouldn't really have to label that. And we're going backwards till t equals 3, and that happens at s equals 0, so we're right back to where we started. T equals 3, s equals 0. So we moved right from 0 to 1, we moved left from 1 to 3, and went from 4 to 0. From t equals 3, our velocity is positive, so we're turning around and going the other way forever now. And I don't really have any points over there, I just know that it goes forever that way. That's our motion diagram. It's an attempt to capture position and velocity and time all in one picture. Part G. Find the displacement of the particle during the first 5 seconds. So that's just where we are at 5 minus where we were at 0. The motion diagram is irrelevant to displacement, right? It doesn't matter how we get there. What's S of 5? Plug in 5 to S. Again, be careful. You got S's and V's and A's all over the place. So make sure you're putting things in the right spot. Let's see, 125 minus, I guess I could just safe stop that and just leave all of that as S of 5 and then subtract S of 0. 5 squared is 25, times 6 is 150. Yeah, I should probably safe stop this at the risk of messing this up. Negative 25 plus 45 is 20. I keep saying that and I keep going. So 20 minus S of 0 we already found. That was 0. So 20, and then this one does say units. So we look all the way back up. S is in meters, so 20 meters. So after 5 seconds, we're 20 meters to the right of where we started. All right, H is a little trickier because the total distance during the first 5 seconds. So I need to worry about, now my motion diagram is going to be very helpful here. Motion diagram. Because I think I'm going to do it this way. I'm just going to get a little table going here. So from 0 to 1, this is intervals now. From 0 to 1, how far did we go? 4. So from t equals 0 to t equals 1, we went 4 meters. From, I should probably have drawn that the other way. From 1 to 3, how far did we go? My motion diagram. From 1 to 3, we also went 4. Not negative 4 because we're doing distance. So just positive 4. And then from 3 to 5, well, let's see. From t equals 3, we were at 0. At 5, we just found that out. That's on this picture. We could put S of 5 on there. It's at 20. And t equals 5, S is 20. Added a point to my motion diagram. Not really to scale, right? But 20 is way out there. So from 3 to 5, we went 20 meters. So all told, we traveled 28 meters. But the trick is there's no way to get that 28 unless you break it up into pieces. And so total distance, at least for now, you almost always need a motion diagram to figure out, well, where did I turn around? And then I can add up my pieces. All right, speeding up and slowing down. That's where speeding up would be A and V have the same sign. Slowing down would be A and V have opposite signs. Okay, I already know something about V. In fact, I'm going to just recopy that V picture down, that V number line down. In fact, it's already color-coded, so I'm going to stick with my color code here. Positive from 0 to 1 and 3 on, and it was negative from 1 to 3. Now I need to do the same thing for the acceleration and kind of look for where they overlap. And you could do this without physically drawing them in the same spot, but I think it's easier if you put them in the same spot. So acceleration was 6t minus 12. So that would be 0 at t equals 2. Now I'm doing that same thing, the number line thing, where we test intervals and see if it's positive or negative. If we're talking graphing, this would be the concavity test, the second derivative test. We're doing motion, so the second derivative is acceleration. So plug in 0 and 3 into acceleration, because I want to know acceleration. So a of 0 is negative. I'm just going to stick with my color convention here. So negative is green. A of 3, 18 minus 12 is positive. Okay, so now I'm like trying to look at both at the same time and see where they have the same color and the different color. So it's speeding up when they have the same. So that would be 1 to 2. And anywhere else they have the same color? So 1 to 2. And then 3 to infinity. And with my colors, like 1 to 2 is speeding up in the backwards direction. 3 to infinity is speeding up in the positive direction. And then slowing would be where they have opposite signs, so 0 to 1, or opposite colors in our case, and 2 to 3. Speeding up, same sign. Slowing down, different signs. Today's assignment is worksheet 2. And we'll do a lot of stuff together tomorrow. So you don't have to do all of worksheet 2 to stay on track, but do some of worksheet 2, and that way you'll be on track.